Welcome to Review Lecture number 9 on continuous random variables. Lecture number 9 in a series of lectures reviewing an undergraduate course in probability and statistics. I'm Chris Mack, your professor for this class. And for the last 2 lectures, we looked at discrete random variables and how to calculate the expectation and variance for those kinds of random variables. Now let's look at continuous random variables. Let's remind ourselves of what a random variable is. Random variables are real valued functions of the outcome of an experiment. So I run an experiment and I get an outcome. And we talked about probability theory and sample spaces as sets of all the possible outcomes of an experiment. Well, what a random variable does is it maps the set to the real numbers so that we get numerical outputs for our experiment. Simple example. I'm going to define a random variable as the height of a UT student. So omega, the sample space, is simply all the UT students, and x represents represents a measurement of the height of a randomly selected UT student. So what kind of a random variable is x? Well, it could be discrete or continuous depending upon how we've defined this. For example, we could round the height measurement to the nearest inch or the nearest centimeter or the nearest something. If we did that, we'd get a discrete random variable, specific numbers, and there would be a limited number of numbers possible. So in this case, it would be a finite set of discrete numbers to make up our sample space. But I can imagine a measurement which allows infinite precision. If I did that, our random variable x would be continuous. It would be a real number that had any possible value along the real number line. Well, in reality, we can't do that. We can't measure to infinite precision, but we can assume that we can, and we can model the measurement process as if it were producing a continuous, real valued output, so that we model this random variable as being continuous. Let's look at this continuous random variable by comparing it to a discrete random variable. As we've seen, a discrete random variable is characterized by, the probability mass function, p sub x. X is our random variable, and the probability that a random variable takes a certain number, little x, is called the PMF. So we can describe the probability of my random variable being between some lower bound a and some upper bound b, as the sum of all the values of x that are between a and b, summing up the PMFs. Well, this is how we think about a discrete random variable. Let's assume, for example, it's heights. And we have discrete values for the heights that we could measure. Now let's take those heights and assume we can measure them to greater and greater and greater precision, so that the distance between all the possible values of x is getting narrower and narrower and narrower along the number line. If we let the distance between values of x go to 0, this is like taking our sum and turning it into an integral. It's a classic calculus move where we start with the summation, we let the numbers that we're summing up become infinite, and the summation of all x values between a and b becomes the integral from a to b. Our PMF turns into what we'll call the probability density function, or PDF, multiplied by this distance between values of x dx. We're essentially letting dx go to 0. The PDF, or the probability density function, is given by the letter F instead of the letter P. We use the same subscript X to represent whatever random variable we've defined. If I define the random variable to be W, then I would have F sub W. Then we replace the summation of our PDF equation with an integral, and we replace the summation of our PMF equation, our discrete random variable equation, with integral. We replace the PMF with PDF times dx. And then whatever equation we had in the world of discrete random variables becomes our equation in the world of continuous random variables. This PDF, or probability density function, is defined kind of in a backwards way from what we just described. The PDF, by definition, is the probability that a random variable x is between a number and that same number plus delta divided by delta in the limit as delta goes to 0. In other words, the PDF is the probability per unit length along the x-axis. And we let delta, the distance between x values, go to 0 to create a continuous variable along the x-axis. From this, we can see that the probability is going to be the area under the PDF curve, because PDF is probability per unit length. So if I have PDF as a continuous function with the x-axis shown here, then the probability that my random variable is between A and B is the integral, or the area underneath the curve between A and B. Okay, if I go back previous slide, we see that right here. The probability that x is between A and B is the integral of the PDF between A and B. So here we just have a graphical representation of that statement. What are some of the properties of the PDF? Well, some of them are very much like the properties of the probability mass function, or PMF. First of all, it is always non-negative. The normalization requires that if I integrate the PDF from minus infinity to infinity, all possible values, I must get 1. That comes directly from the normalization axiom of probability. And the probability at a point must be 0. If I have a continuous function, the area under a point is 0. Only over a range of x values do I get a probability that is non-zero. Give you a simple example, the uniform probability. If I have a uniform probability between A and B, then for a discrete random variable, my PMF takes on identical values for all the values of x where it's non-zero. For a PDF, a continuous random variable, my function looks like a square wave. It's 0 outside of A and B, and within the range from A and B, it must have a value of 1 over B minus A. How do I know that's true? Well, the normalization property requires that to be true. Recall that the area underneath this curve for all values must be 1, and the only way for the area of this rectangle to be 1, since it goes from A to B along the x-axis, is to have a y-axis height of 1 over B minus A. All right, now that we have some idea of what a continuous random variable is and how we characterize a continuous random variable using a probability density function, let's compare expectation and variance for a discrete random variable to a continuous random variable. As we saw last time, for a discrete random variable, the expectation, which is nothing more than the mean, is the value of x multiplied by the probability that that x value will occur and then summing up over all possible x values. It's the weighted sum of all of the x values. The variance is the weighted sum of the difference of x from its mean quantity squared. So it's the sum of the squares of the deviation from the mean, weighted by the probability that that x value will occur. Well, we can convert these definitions of expectation and variance to continuous random variables by doing the formula I mentioned before. Convert our sums to integrals and replace the PMF with the PDF times dx. And you can see that's exactly what I did here, here, and here. Now expectation is the integral over all values, which is, because it's a real number from minus infinity to infinity, of x times the PDF. The variance is the integral over all values of x minus its expectation quantity squared times the PDF integrating with dx. So just like we could calculate for any discrete random variable distribution the expectation and variance of that random variable, if we know the distribution, if we know the PDF of our continuous random variable, we can also calculate the expectation value and the variance using these formulas. Let's use our uniform PDF as an example. The uniform PDF between A and B, 0 outside of this range, has a PDF equal to 1 over B minus A when I'm in the range and 0 otherwise. We've already seen that. Now let's calculate the expectation for this random variable. Well, we simply plug it into our formula. We're integrating over all values of x, but anywhere below A and beyond B, it's 0, so I can confine my integral to go from A to B. I take x and multiply it by the PDF. The PDF is simply 1 over B minus A, and then I integrate, and I get the answer, B plus A over 2. Well, I bet we would all expect that. It's a symmetric PDF, so the mean value must be exactly in the middle, B plus A over 2. But what about variance? Variance isn't necessarily as intuitive to grasp exactly what its value might be, but we can calculate it quite easily. We take our definition, apply it using this particular PDF, we plug it in, and we get an answer, B minus A squared over 12. Again, not necessarily intuitive that it would be divided by 12, but that's the result. And this variance of a uniform random variable can come in quite handy whenever we have a process that produces uniform uncertainty over a specific range. Before going on to a different continuous random variable, let's talk about the cumulative distribution function. We defined what the cumulative distribution function was for a discrete random variable a couple of lectures ago. Now let's look at the CDF, cumulative distribution function, for a continuous random variable. I'll use capital F to represent the CDF. The random variable is x, and the CDF at a value b is defined as the probability that the random variable is less than or equal to b. In fact, this definition of the CDF is the same for either a continuous or a discrete random variable. But how we calculate it is different. I will use here an integral from minus infinity to b of the PDF, probability density function, times dx. And of course I could arrive at this formula by taking the discrete random variable formula, replacing the sum with an integral, and the PMF with the PDF times dx. One of the advantages of knowing the CDF, if we have a, say, an analytical expression for what the CDF is, we know that the CDF is monotonically non-decreasing, and so it's very easy to calculate the probability that some random variable is between two values within the range from A to B. It's simply the difference in the two CDF values. So once I know the CDF, I can calculate the probability over any range whatsoever by simply taking the difference between two numbers. And it's also interesting to note that the PDF is simply the derivative of the CDF. Now, let's look at what is by far the most important distribution for a continuous random variable. It's called the normal distribution, or Gaussian distribution. Numerically, the formula for a Gaussian distribution, hopefully we've all seen it before, is this. 1 over the square root of 2 pi times sigma. Sigma is the standard deviation. And note that sigma is not underneath the square root. Sometimes you'll see this formula as sigma squared, where the sigma squared is underneath the square root. Just make sure you get it right either way you write it. Then we have e to the minus x minus its mean, quantity squared, divided by 2 times the variance, sigma squared. So I have two parameters. I have mu, the mean of the distribution, and sigma, the standard deviation, or sigma squared, the variance. We then describe notationally the Gaussian distribution using the letter n to represent the normal distribution with the two parameters mu and sigma squared. The cumulative distribution function is the integral of the PDF from minus infinity to whatever x value we're interested in, and the integral of a Gaussian produces an error function. And so here's the formula. Error functions sometimes are available on your calculators. They're certainly available in spreadsheet programs and other pieces of software, so it's not hard to calculate an error function if you need it. The expectation of this random variable, a random variable that follows the PDF of a Gaussian distribution, the expectation is mu. We've already defined mu as the mean of the PDF, and the variance of this random variable is sigma squared. The curve, the very common bell curve shape. It's symmetric. Of course, the mean's right in the middle. The spread represents the standard deviation, or characterized by its variance. Now, it's often very common to normalize our normal distribution. That's a kind of a strange way of expressing it, but we define something we call a z-score. We take our random variable x and we subtract off the mean of the distribution, then divide by the standard deviation of the distribution. If x, our random variable, is normally distributed with a mean mu and a variance sigma squared, then z will also be a random variable that is normally distributed, but with a mean of 0 and a variance of 1. We call this a standard normal. And it's very convenient often to take whatever variable we have that's normally distributed and convert it to a z-score, convert it to a standard normal distribution. This is a special case of an important property of a normal distribution. A linear function of a normally distributed random variable produces a normally distributed random variable. If y is alpha x plus beta, so x is a random variable that is normally distributed, then y will be a random variable that's normally distributed as well. Its mean will be alpha mu plus beta, and its variance will be alpha times sigma quantity squared. Since linear functions of random variables occur quite frequently, this is a quite useful identity to remember. Now, we've talked about the uniform PDF, we've talked about the normal PDF. But there are many, many, many important PDFs that are useful in certain circumstances. The exponential distribution, Gaussian distribution, students' t distribution we'll use quite a bit. Chi-squared distribution we'll use later on in these lectures. Log, normal, beta, gamma. We won't talk about all of them. We won't talk about many of them, as a matter of fact. But under various circumstances, for various kinds of problems, experiments, you may need to use one or more of these distributions. Wikipedia, I find, is a very good source for information about these distributions and their properties. You can just look up the chi-squared distribution and very quickly get the equation for the PDF, for the CDF, for the mean, for the variance, and many other properties of these distributions. And finally, to relate a PDF to something we talked about very early when we looked at characterizing univariate random variables in our discussion of descriptive statistics, we talked about histograms. Well, histograms are very often used as ways of comparing to PDFs. You might think, is my data randomly distributed according to a Gaussian distribution? Well, I might look at the histogram, compare it to the shape of a Gaussian, and try to evaluate, that looks like it could be reasonable, or, oh no, that doesn't look very good at all. So we often use histograms in this way. All right, let's review lecture number 9. What have we learned? As always, you should be able to quickly and easily answer these questions. If not, please go and review the material again. How are discrete and continuous random variables related to each other? How are PDF and CDF related for a continuous random variable? You should know how to calculate the expectation and variance for any PDF that you might be given. And finally, what is the normal distribution, and what are some of its most important properties, as we've discussed so far? Well, that's the end of our lecture on continuous random variables and our 3 lectures on random variables. Next time we'll begin talking about how to use our knowledge of random variables and their distributions in the field of statistics. Till then.